Hello and welcome to the lecture on correlation and regression. I'm going to try and make this lecture a little bit quicker than most previous lectures, and next week's lecture will be actually longer. This is a topic that we've talked about at various times throughout, but we're at a point now where we need to look at it in a little bit more detail. So I will go into it, but I'm probably going to go through it a little bit faster than I have been. So if you have any questions after you've watched this, feel free to email me. Okay, so in this lecture, we're going to look at correlation, specifically linear correlation and regression. We're going to start by looking at a scatter plot. We're going to go from there into sum of cross products, covariance, those types of things that lead us to the correlation. So we've kind of talked about this a little bit before in ways. What we're looking at here is the relationship between two variables instead of just each variable independently when we're looking at sum of squares and standard deviation. Then we'll look at linear correlation. We'll go from there into coefficient of determination, and we'll then from there go into the more complex regression, standard error of estimate, estimating population error variance, and we'll finish up with some stuff on z-scores, even though I'm not going to spend too much time on that because I won't test you, or it's not on the homework or anything. Okay, so let's start talking about regression and correlation. Let's start talking about when we've got two variables and we're looking at a relationship between the two variables. We're not doing it like we did with the t-tests where we're looking at the difference between two variables. Now we're looking at how two variables are related to each other. And this goes to a lot of quite a bit of similarity to what we covered last week in the chi-square test of independence. But that was for categorical variables. Now we're looking for continuous variables and how continuous variables relate to each other. So the first step, though, is always to look at a graphical representation. Now you can use stats packages to get these graphs, but why do we look at a graphical representation? It's something we'll talk about at the end of these slides, but you can actually have relationships between variables that don't show up when you do correlation. Why is that the case? Because correlation is looking at a linear relationship. And if you've got a nonlinear relationship between variables, that's not going to show up when you do correlational analysis. So you might have these two variables, you run correlational analysis, you don't get a relationship found, so you go and report that there's no relationship between the variables. When there is, it's just that there's no linear relationship. And we use a scatter plot to do this to get a visual idea of what's going on with the data. Here's an example of the scatter plot. Each point, each dot represents an x and a y value for the whatever it is we're looking at. So each dot is an individual, and on the left is their quiz total, on the bottom is their exam total. So it's each individual's has one dot, and it's the intersection of where they are on their two scores. Another example here, we've got temperature and aggression. Each of these would possibly be a day. So the temperature, the high temperature for that day, and the amount of aggression that an individual does. Stuff like that. So when we're making our scatter plot, it's a lot like our previous charts. We label the x and y axes. We put the scale values on each axis. For each person, there's one data point. Very simple stuff. Not much I need to talk about here. Like I said, this is going to be a quick lecture because a lot of this is just stuff that should be pretty self-explanatory. Okay, once you've done that, once you've graphed it out and it looks like there might be a relationship, a linear relationship between the two of them, we do a correlation. The correlation coefficient is a stat that's used to basically express quantitatively the extent to which two variables are related. So I'll come back to that when we've done it, but when we're looking at it, it's basically the correlation is telling us how much of one variable is accounted for by the other variable. To do this, we use the Pearson product moment correlation coefficient. Technically, we're only supposed to use it with interval ratio level data, so along those lines, that's an assumption that you should fall under, is you should only be using this with interval ratio. As I said when I was explaining it last week, sometimes people will do things with ordinal data, such as Likert data, and on this, but you're supposed to only do it with interval and ratio. So this Pearson product moment correlation coefficient, very long name. We tend to just call it the correlation coefficient, the correlation, or Pearsons R. It's a measure of the relationship between relative scores. So in a way, it is very similar to z-scores, but it's actually measuring the relationship between two different z-scores in a way. It's not directly that, but that's in a sense what we're doing. You first have to standardize scores, because you can't, if you've got two scales that are very different, correlations don't work with them. So it's standardizing these scores and looking at the relationship between those standardized scores. The range is going to be between -1 and +1, and it's going to tell us direction and magnitude. So what do I mean there? Direction, a positive score is going to be a positive correlation. As one goes up, the other score goes up, the other score goes up. I'll talk about that more on the next slide. Negative is a negative correlation. As one score goes up, the other goes down. So that's how it tells direction. Strength is also important. That is, the farther from zero you get, the stronger it is. And that's one thing I like to ask questions like this on quizzes, on Part A's, and give a couple correlation values and ask you which one's stronger. Well, the one that's stronger is going to be the one that's farther from zero, because it's not the one more positive, it's the one furthest from zero. So a correlation of -0.9 is stronger than a correlation of +0.5. That is because it's farther from zero. Another way to say it is closer to 1 you get, the stronger the relationship is. As I already said, positive relationships, they're between 0 and or above 0 up to 1. That is where one variable goes up, the other variable goes up. Negative relationships are less than 0 all the way to -1. That's where high scores on one variable mean low scores on the other variable. You see 0 is not included here because 0 means there's no relationship, no correlation. Let's get into, though, how to calculate out correlations. How do we calculate it out? One way we do it is with what's called the sum of cross products. So if you remember sum of squares, the definitional formula for sum of squares is here. It's the sum of x minus the mean, all of those squared, which ends up being written out as the sum of x minus the mean times the sum of x minus the mean, or the x minus the mean times x minus the mean, then all those scores are summed. So that's another way to write it. Sum of cross products is similar, but now it's going to be x minus the mean times y minus the mean for each score. Then we sum all of those. I'll give you a definitional or a computational formula in a minute, but the definitional formula of the sum of cross products is it's the sum of the product, all the products of cross values. So sum of all of the x's deviation from the mean times its corresponding y deviation from the mean. If you recall, variance is equal to sum of squares divided by n. Well, the covariance is going to be in a very similar way. It's going to be the variance of the differences between the two variables. So we compute a covariance in a very similar way to the variance. The covariance written as SXY. So in a way, the square isn't there. You don't have to worry about that. SXY is just talking about the covariance, and that is equal to the sum of cross products, the sum of squares xy. That was, you'll sometimes see this sum of squares xy written as SCP, sum of cross products. So it's the sum of cross products divided by n. And this is your full definitional formula, though I will give you computational formulas that are much easier because you don't want to take each x value away from the x mean, each y value away from the y mean, and multiply. That's just the same reason you don't do that with the sum of squares. It's easier to do it other ways. So when we do a z-score, it's a standardized score. So we've done this before. It's x minus the mean divided by the standard deviation. What in a sense we're doing there is we are standardizing them. We are making them all so they're comparable. Well, we do a similar way with the standardized covariance. Another way to call the linear correlation or the Pearson product moment correlation is standardized covariance. And we do this by taking our covariance and dividing by the standard deviation for x times the standard deviation for y. So you have to calculate out standard deviation for x and standard deviation for y separately. But so one way to get the r is to take the covariance and divide by the standard deviation of x times the standard deviation of y. I hope that is pretty self-explanatory. Like I said, I'll give you some computational formulas in just a minute, but this gets us to what actually is the correlation. The correlation R, I'm sure you've all seen it before, the Pearson product moment correlation, Pearsons R. All it is standardized covariance. So this is the definitional formula we were just looking at. One way to calculate it out, and this is once you reduce, you can get rid of some of the ends and stuff like that by the way it works out. So it's actually equal to the sum of cross products divided by the square root of sum of squares x times sum of squares y once you reduce and get rid of all of the ends that you can reduce out. So what you see on the left is the definitional formula. What you see here is the computational formula. So if all it is the sum of cross products divided by the square root of the sum of squares x times the sum of squares y, well, you can use the sum of squares x formula, the sum of x squared minus the sum of x, that value squared, divided by n, times the sum of squares y, which is the same formula except with y's, and then you can use the computational formula for sum of cross products, and that is here. And that is the sum of x, all the x's times y's, so sum of x, y's, minus the sum of x times the sum of y divided by n. You see that sum of cross products computational formula is actually very similar to the sum of squares x formula. So this is a much simpler and easier way to do it. Then in this way, once you get your x's and your y's, all you need to do is square your x's, do your x's times your y's, square your y's, so square your x's, square your y's, do your x's times your y's, and you can actually do everything in this formula from that. So that is your computational formula for Pearson product moment correlation, Pearsons R, the correlation coefficient, the correlation, all different ways to say the same thing. Let's talk about two other things that are related to that though. The first is the coefficient of determination. Coefficient of determination is also called R squared. To get the coefficient of determination, to get R squared, all you have to do is take your R that you had from that previous formula and square it. And that gets our R squared. What's important here though is R, so R is still, when we just have R, it's a standardized covariance, but it's still not something we can really interpret that well. Once we square that, once we get our R squared, it's actually something we can interpret. And R squared is measuring the relationship between x and y. And this is something I guarantee you, I'm telling you right now, I hope you're watching this lecture, I guarantee you I'm asking this on part A of the exam coming up as a short answer. What is R squared, or what is the coefficient of determination? What does it represent? And it is basically a measure of the strength of the relationship between x and y, or another way of saying it is it's the percent of variance in one variable that can be explained for in the other variable, or counted for by the other variable. So it's the percent of x accounted for by y, or the percent of variance in x accounted for by y. And it's the percentage of variance in y accounted for by x. It's both the percentage of variance in x accounted for by y and the percentage of variance in y accounted for by x. That is because we cannot determine causation in correlation, so we just say it's the percentage of variance in one variable accounted for or explained by in the other variable. So the coefficient of determination, if you had to interpret it, that would be the way you'd interpret it. And it's very easy to calculate out once you've got r, because all it is r squared. And then finally, we've got the coefficient of alienation, also called the coefficient of non-determination. This is the percent of variance in one variable that is not accounted for or explained by the other variable. And all you have to do to calculate this is do 1 minus r squared. So if your r is, let's say your r is 0.8. So if your r is 0.8, your r squared is going to be 0.8 squared, which is 0.64. So your coefficient of determination is 0.64, and you're basically saying that 64% of the variance in x is accounted for by y, and 64% of the variance in y is accounted for by x. You're also saying 1 minus that 0.64, your coefficient of alienation is 0.36, so 36% of the variance in x is not accounted for by y, and 36% of the variance in y is not accounted for by x. Here is an example of all of that. I'm not actually going to go through all of this because you've got it all here, but let me go through it very briefly. So you've got your x's, your y's. Those are the values you were given initially. You also have to calculate out x squares, y squares, and x times y's. I said that earlier. But you've calculated out all of those. Now you have your totals down here at the bottom. You just have to plug those in. So the sum of cross products is the sum of x, y. So it's that 28 there. The sum of x, which is 13. The sum of y, which is 14. And n, which is 4. You plug those in, and you get a sum of cross products of negative 17.5. I can tell you right now, if your sum of cross products is negative, your r is going to be negative. And you can look at just these values and see that as x goes up, x starts low, then goes up, y actually goes down. So low x values are associated with high y values, high x values are associated with low y values. Sum of squares x is over here, sum of squares y is down here. Again, you just have to plug in values. Take and plug those values then into our equation, and we get a Pearson product moment correlation of negative 0.8383. I kept it to 4 decimal places because it's not going to get to the last one, but if you just put this negative 0.84, I'd be fine with that too. So that's our r. Our r squared is going to be that negative 0.83 squared. But essentially this negative value, let's go back to r real quick. It's a negative value, means there's a negative correlation. It means as x goes up, y is going to go down. It also is way closer to 1 than 0, so it's going to be a strong relationship. And when I say 1, I mean negative 1. It's closer to negative 1 than 0, so it's going to be a strong relationship. The cutoffs between weak, moderate, and strong relationships are kind of arbitrary. It actually depends on the field you're in. STEM disciplines, you have to be much closer to 1 and negative 1 for it to be a strong relationship. Social sciences, a 0.3 might be considered a strong relationship. So we calculated the coefficient of determination, which was that r squared. We get 0.70. We then take and do 1 minus that, and we get, for the coefficient of alienation, we get 0.30. Let's interpret these. The coefficient of determination, it's essentially saying 70% of the variance in x is accounted for by y, and 70% of the variance in y is accounted for by x. Coefficient of alienation, 30% of the variance in x or 30% of the variance in y is not accounted for by the other variable. So now that we've talked about correlation, and that should be pretty easy stuff, let's actually take it one step farther and look at regression. So what is the difference between correlation and regression? When we're talking about correlation and regression, there is a difference. First of all, correlation describes a relationship. So we just got done talking about it. Describes the strength of the relationship, the direction of the relationship, all of that. So correlation is describing the relationship. Regression is used, on the other hand, to predict. Regression uses past information about the relationship, which is the correlation's part of that, past information about the relationship, in order to make predictions about what a score will be based on new information, based on whatever it is we're looking at. The regression equation is a very simple equation here. I'm trying to keep it short, but this is the standard linear equation, and that is y predicted equals a plus bx. What is going on here? Well, a is going to be our slope. No, that is incorrect. Ignore what I just said. A is going to be our y-intercept. We'll look at that more in the next couple slides. B, on the other hand, is going to be our slope. So you might see this equation written differently. Mx is sometimes used here, but in statistics we use this equation. Y prime, y predicted, which is the value we're going to predict for y, equals the y-intercept plus the slope times x. And x is a value that'll be our predictor variable, y will be our predicted variable. So you'll be given an x and need to predict y from it. But to get there, you first need to calculate out the regression equation. So you need to figure out the slope and the y-intercept based on past information. So the first formula we're going to look at is the slope formula. This formula is the longer of the two formulas. And this you see here the definitional formula for it, but the slope is basically, what the slope means is for every increase in x, that's how much y changes. Y, if it's a positive slope, that's how much y increases. If it's a negative slope, that's how much y decreases. So you see here, the slope is going to be very closely related to the correlation, because just like the correlation, you're going to have positive or negative in the direction of the relationship. So what you need to get this is you need the correlation, and you need your standard deviation of x and your standard deviation of y. Another way to calculate it is if you have your covariance, you can just take your covariance and divide by sum of squares x. That is because basically it's a index of the difference between the covariance and the sum of squares x, or in covariance and the variance of x. You take out the ends and you just get the sum of squares xy, the sum of squares for the covariance, divided by the sum of squares for x, the sum of squares for the variance. So if, let's say you had a r of negative 0.72 and you had a standard deviation of x of 2 and a standard deviation of y of 1.63, you could calculate that out by doing negative 0.72 times 1.63 divided by 2, and in this case you get a slope of negative 0.58. That's the definitional formula. I'll actually give you the computational formula on the next slide, which is much better. And you should already actually know the computational formula because you've got the computational formula for these two. So you just need the computational formula you just need to apply that to this problem. Here you see that, again, the definitional formula, much harder to calculate. Computational formula, it's just going to be that sum of cross products computational formula divided by the sum of squares x computational formula. The same thing from the correlation we just talked about earlier. So now that you've got the slope, you can calculate the y-intercept. The y-intercept is, in a sense, where the regression line hits the y-axis. That's the best way to explain what is the y-intercept. The y-intercept is where the regression line hits the y-axis. The formula is equal to the mean of y, so you need to get the mean of y, minus the slope times the mean of x. So you need to get the mean of x as well, but you notice here you need the slope as part of this formula. You cannot calculate out this formula without the slope, so you need to get the slope first. So it's the intercept of the regression line is just the predicted value of y when x is 0. So if x is 0, this would be the y-intercept would be when x is 0 where what y is. And that is, in a sense, again, where the regression line hits the y-axis. Here's an example. I plugged it all in here. I'm not going to spend a lot of time on this, just like I didn't on the last one, but you see you've got your x's, your y's, your x times y's, your x squares, your y squareds. It's all of the stuff you needed for correlation. Well, sorry about my cat meowing in the background. He's a hunter, and when he starts hunting stuff, he meows like that. So we can plug in everything here, though. The sum of xy, which is 1023, minus the sum of x, which is 67, times the sum of y, which is 72, divided by n, which is 5. And then you just have to divide that by the sum of squares x. You get a final answer for slope of 0.2070. Again, I kept it to 4 decimal places just because it's an intermediate step. Y-intercept, the a, you need to take the mean of y, which is 14.4. I do not have it on this. Let me just put it up here. And the mean of x, which is equal to 13.4. And you plug in the slope into that, and you get a y-intercept of 11.62. So our final y equation, and this is what I expect you to write. I expect to see this right here. When I ask for what is the regression equation, I expect to see this y prime equals the a plus bx, in this case 11.62 plus 0.21x. And below this, I just have an example of, well, what if I wanted to know what is y predicted when x equals 6. So it shows the power of the regression equation because what it is it's a prediction tool. So all you do here when you're asking, well, what's the y predicted when x is a certain value, you plug in that x value. So here we plugged in that 6 for x, and you get an answer of 12.88. So the predicted y when x is 6 is 12.88. So just some kind of finishing up things and a little bit more in-depth into kind of what's going on here. The regression line, the line you use if you draw so if you did 2 different points on, if you let's say took 6 and we took 12 as our x's, and you drew a line between those and extended beyond those, that would be the regression line. What is going on here is the regression line is also called the line of best fit. That is because there's always going to be error. The line has to be straight, but distributions are almost never perfectly straight. What do I mean by that? Well, let's say we've got some dots here, and we take and we draw the line of best fit. We figure this out, and we get the line of best fit. And the line of best fit ends up being that blue line there. Well, one thing to consider here is that not every one of our actual points is on the line of best fit. You've actually got differences here. So what regression is actually, and these differences are all in green, these are differences between the actual data points and the line of best fit. What the regression line does is it tries to minimize, because all of that green is error. The green is error. What the regression line is trying to do is minimize that error. It is giving you the line that is of best fit, meaning it has the least amount of error, meaning it has the least amount of green. If I move that line somehow, let's say I moved it and I tipped it down or I tipped it up, then the green lines that you see there would increase Some of them would increase, some of them would decrease, but the overall green lines would increase on average because it's not the line of best fit. The line of best fit has the least amount of error, the least amount of green lines, the least amount of differences from the regression line. The next thing I'm going to talk about is variation. And I'm going to talk about this because this is going to lead into next week. Next week we're going to talk about ANOVA. In ANOVA, you actually look at parceling out variation. And when we're doing regression, we talked earlier about explained variability and unexplained variability, which is our R squared and our coefficient of determination and our coefficient of alienation. But another way to look at this, another way to, and it's not, you're not calculating out the same thing, but another way to look at what's going on here is when we parcel out variation. So again, we just looked at the fact that not all points are on the regression line. Well, what is different from the regression line? That is variation. So the variation is the differences from the regression line. And to calculate out the total variation, we have to do the sum of squares total. And the sum of squares total is the sum of each y. And I didn't draw it out, but I drew it out on the previous slide where there's differences, but let me try and explain it without drawing it out here. It's the sum of each y value minus the mean of y, and we're going to square that. So if we took our y's and we took the mean of them, and we took the difference from each y from the mean, that is our total variation, and that is our sum of squares total. However, our explained variation, which is also called our sum of squares regression. Regression in this case means the explained variance. That's what the regression equation is doing. To get that, we take the sum of each y predicted, so the y predicted for each x value, subtracting the y mean and squaring that. As you can see here, there's not easy ways to do that. And then finally, you have the unexplained variance. This is the sum of squares residual. The residual is the unexplained variation. It's also another way to say error. And this is the sum of each y minus the y predicted squared. So to get these, when we put it all together, the sum of squares total actually equals the sum of squares regression plus the sum of squares residual. So sum of squares total, that's the total variation. The total variation is parceled into explained variation and unexplained variation, so you're splitting it up. So the sum of squares total equals the sum of squares residual plus the sum of squares regression. This is actually something that's going to come up again when we're doing ANOVA, because this is a key component of ANOVA. That's why I'm bringing it up now. I'm not going to make you calculate these out. There are other ways to calculate these that become a little bit easier, but they're either way, it's a complicated, long, drawn-out process. I'm not going to make you do it for this week. When we do ANOVA next week, you are going to have to calculate out sum of squares residual and sum of squares regression, but the computational formulas for those are much easier than this. So what does this matter? This gets us to our standard error of the estimate, which I had initially asked on the homework. I'm not asking any more on the homework. I took it off. If you downloaded the homework early on, then you'll need to go back and see that the last question has been taken off. I'm not going to ask you this on the homework. I'm not going to ask you on the exam. I just want to point out what's going on here. So this is going to be sy.x. This is the standard error of the estimate around the regression line. There's formulas you can use for the population and sample. Just note that the standard error of the estimate is very similar to the standard error of the standard error of the estimate in one sample, but now it's going on with two samples. And it's basically the standard error of the estimate, or the standard error of the prediction is another way to say it. Another way to calculate out R squared, and so the coefficient of determination and the coefficient of alienation, is actually to do sum of squares for R squared is sum of squares regression divided by sum of squares total. The coefficient of alienation is the sum of squares residual divided by sum of squares total. So this is essentially saying, when you look at this, This is showing you how another way of what's going on. So we calculated out the coefficient of determination before by getting to r and just squaring that. But really, what does r squared mean? I talked about it in terms of the words that it's the percent of variability or variance in x accounted for by y. But this is actually showing that out. How it's actually working is it's a ratio. It's a ratio of the explained variance to the total variance. The r squared is the explained variance here, the sum of squares regression, as a ratio to the sum of squares total, the total variation. So in a sense, it is telling you the same thing in this way, in a formula way, as the words before. It is the ratio of the percent of, or it's the ratio of the explained variance to the total variance. So in a sense, it is the percent of the variability in x that's explained for in y by y. And the coefficient of alienation is the unexplained variance to the total variance. So it's a ratio of the unexplained variance to the total variance. So just kind of a way to see that there's multiple different ways to get to the same answers, and this kind of shows what is going on in that problem. Just one last thing before we get into just some caveats or warnings. I do want to talk about the regression with z-scores. Regression with z-scores is very, very easy. It's one of the easiest things you'll do. I'm not going to even put it on the homework or the exam. But basically what it comes down to is if you know your correlation, you can take and get a y predicted just by taking the z-score for your x. So take the z-score for your x value, multiply it by your correlation, and you get your predicted y value. Very simple. So if you know, and since if you know both a mean and a standard deviation, you can convert back to raw scores. You can convert it to a z-score, multiply it by the correlation, and convert it back to a raw score. Very, very simple thing to do when you're talking about it when you're dealing with z-scores. Okay, 2 caveats at the end. I told you I'd come back to this. A Pearson correlation coefficient, Pearson product moment correlation coefficient, Pearsons R, the correlation, only looks at linear relationship. It does not indicate if there's a nonlinear relationship or not. One of the most classic examples of a nonlinear relationship is anxiety and performance. That is, those who have low to no anxiety tend to do poor. Those who have high anxiety tend to do poor. Why is this? Because if you have high anxiety, you're thinking too much about your anxiety to do well on a test. If you've got no anxiety, you don't even study for the test because you don't care. It's moderate amounts of anxiety because they press you to do better, presses you to study, it presses you to think about it leading up to the test. But once you're taking the test, you're not so overwhelmed that you're still able to take it. So a moderate amount of anxiety tends to do better on performance. This is a nonlinear relationship. If you ran a Pearsons R on the relationship between anxiety and performance, you would get no relationship, no correlation. That's because this relationship is nonlinear. You would need a different formula to look at this, and this is why we always, always, always plot out relationships. We don't just look at Pearsons R and say, oh, there's a correlation, oh, there's no correlation. We need to look at the actual graphed out, the scatter plot to see if there is. So no correlation does not indicate no relationship. No Pearson's product moment correlation doesn't indicate no relationship. And then the final thing, and I shouldn't even have to say this, but I'm going to because it just needs to be said over and over and over again. So when I say I shouldn't need to say it, I shouldn't need to, but I need to because it needs to be said. That is, correlation does not imply or mean causation. Just because 2 variables are correlated, just because 2 variables are related, does not mean one is causing the other. There's correlations between social status and health. Does that mean social status causes higher health? No, not necessarily. Does that mean higher health causes higher social status? No, not necessarily. We need to examine it deeper to find causation there. Self-esteem and academic achievement are both correlated, but is one causing the other? No, it's actually likely that that's a third factor causing an increase in both, because if there's a correlation, there's actually 3 different possible explanations. That is, yeah, X may be causing Y. or y may be causing x, or some third factor, not even x or y, just some third factor might be causing both. We look at that first one, social status and health. Wealth causes an increase of social status, and it is related to an increase in health. So wealth causes an increase in both of those. So it just shows that there's a third factor that could cause both of them. So and what's actually interesting is some relationships are reciprocal. That means both x is causing y and y is causing x. So there's even more than just these three to look at and consider. Okay, I kept that lecture pretty short. If you do have any questions, please email me and let me know. Thanks. Come on back.